total variation distance. So you have two distributions, two probability distributions, and you're trying to understand how far apart they are from each other. Maybe for like a concrete example, you might have, let's say, um, data about how many siblings each person in a specific sample, maybe in your class, how many siblings each person has, and like let's say you sort of have like those that have one sibling, two siblings, three siblings, four siblings, and then maybe those who have maybe five and above. So let's say you have here 0.2, here 0.4, then 0.1, that'll be total is 0.7, so 0.2, and then maybe like 0.1. So like you carry out an experiment and you find that in the class this is the proportion that you're having, and you want to use this sample, the class that you have, to sort of make an estimation or a generalization of how it is maybe in the whole school. But you only have data from this sample, and after doing that, you sort of maybe somehow you got your hands on the data of the whole school, and you also come up with actually the exact figures, not just this. In that way, you probably would end up with, and really, for this specific data, that's sort of like a discrete distribution, but just for illustration, I'm going to draw a graph as it were continuous. Let's say this a certain distribution gave data which was maybe a curve like this, and then another one gave data which is maybe a curve like this. So like total variation distance is how far they vary from each other, and like so basically you sort of have two distributions and each has a different parameter, like like that different parameter results into that distribution that you see. So there is a general formula of calculating that, which is right here. I mean, not exactly very informative, but I'm going to prove and show how it's actually used, which is really you find the absolute value of the maximum difference between these two distributions. Well, this same formula is written in another form which we actually use for calculation, which is something like this. Takes an element of a sample space, then we find the absolute value between p theta of an event A minus p theta star of an event A. So like basically, like so, I'm going to. So basically, you're having a distribution here. In this distribution, you have these values for the different numbers, for the different random variables. And then for this one, you have these numbers. So you calculate the difference between these two. 1/2 minus 1/8, it gives you minus 3 out of 8. An eighth minus 3/8 gives you minus 2 out of 8. It's actually positive. A quarter minus 8 gives you a quarter. And this one here, an eighth minus that gives you minus 2 out of 8. Absolute value here is 3 out of 8, 2 out of 8, 1 out of 4, and 2 out of 8. So this formula basically tells you, you look at every single point and just plug in the sum of the absolute values here. This will be 3 out of 8 plus, that's 3 out of 8 plus 2 out of 8 plus 1 out of 4 plus 2 out of 8. So it'll be 5, 6, 8. This will end up giving you a half. That is 5, that's 8, that end up giving you a half. So actually, how you actually use this formula here, where you maximize the sum of this difference. I'm going to explain that concept after I derive this formula. So let me just create more space and make a sum and derive this this formula that we have here. So the formula is it's a half into probability and theta of an event, let's say an event A, minus the probability under theta star of the event A. Yeah, that's a formula. So basically, how this formula is derived is we split so as you saw when you had our table, we had some values that were positive and some values that were negative. So what we are going to do is we are going to split those values into positive and negative. So we're going to say for the event where A is positive, let me use a different marker. We're going to have an event which we're going to call A plus. So instead of using P theta and then P theta star, I'm just going to call this PA, probability of A, and then I'm going to just call this, I'm just going to use Q A to denote the different distributions. So basically, in order to have a positive difference, which I'm going to call the event A, I'm going to have event A to be such that it's going to be the omega, which is really omega is an element of a subset. Omega is an element of an element of a subset such that the probability of omega is greater or equal to under this distribution P is greater or equal to the probability of omega under this other distribution. And then the A minus is going to be where omega is an element of our sample space such that the probability under P is less or equal to the probability under Q. So that means why it's negative is because you're having P minus Q that P minus Q when Q is greater, so it gives you a negative sign. So basically, what you already know for any probability distribution, the summation. So if you have the distribution under P of omega, and it's touching omega being an element of our sample space. So basically the summation of this whole thing is going to be equal to 1. Same thing for the distribution of under Q, still omega, an element of our sample space. So basically for both of them, because they're both probability distributions, they're going to all equal to 1. So in that case, since they're both equal to 1, when I make a summation of let me just put under this and then this. So omega, an element of that. So when I actually subtract them, this sum is actually going to be equal to 0 because, as you can see, all of them both equal to 1. So when you actually subtract them, it's going to equal to 0. So basically, what I'm going to do, I'm going to split the parts where, like the positive ones. Let me write something like this. So basically for we said A plus is where this P is actually greater than Q. So basically we are having P minus, and then we are going to have also omega, an element of A. Nice, and it's A minus Q. This is still equal to 0. So basically, we have just split them into the ones where P is greater than Q, and the ones where Q is greater than P, where A is actually negative. So maybe to explain it, because if you understand this step, everything else is going to be really easy. As you saw, we had our table, and at certain points you saw that the distribution under the first one was greater than the second one, and there we had positive values. And then at another point in the table, you saw that the distribution under the second one was greater than the first one, so we had negative values. So basically, that's how we split this. And then we know from the distribution of any, from the definition of any distribution, that when you sum up all the probabilities, they all equal to 1. So that means when you subtract them, they must equal to 0. So what we have done here is we have split this, we have split and we have put together only those that are positive and only those that are negative. So that means, and I'm going to have to create myself more space. That means that I can actually take one on the other side. So like basically, you can have this omega, an element of A plus. So you're having this minus Q. This is equal to basically negative of an element of A minus so we put the negative sign there. But maybe let's just extend here. So basically, I'm going to like this thing here. In order to make this negative disappear, I'm going to bring this Q in and put it before the W. So basically, it's going to be something like this. This is W, an element of A plus. This is P minus Q. This is equal to. So I said that. Okay, this is. Minus P. So basically, we put this before that. So we're going to denote. This is like a difference in them. We're going to denote this to be delta, and I think you see it. They're basically equal. So that equals delta. They're all equal to delta. That means when you consider this, that these in this form Q minus PW, it's actually equal to delta. The fact that you are considering absolute value, when we have something, the fact that you are considering absolute value, that means it's not going to matter in which order these are placed, and that is what leads to it's sort of like we are summing things twice. That's why we introduced the half, because what we're interested in is this delta, the small change. That's the total variation distance between these two distributions. So yeah, I hope that actually made it make sense. Maybe to sort of if you actually play back the video and you see where we started from on the table and you try out, you actually can just basically so because those that are negative are basically equal to those that are positive. So basically you can just look out in the table for where there are positive values. Just add them up, you don't even need to divide by 2, and you'll have your delta. Yeah, so that's it. Maybe just to sum up, let me just sum it up all. So basically, to evaluation distance, you're trying to understand how far one distribution is from the other. And it has a formula where you just multiply a half by the absolute difference between all the points in the distribution. In this video, I have shown an example where we're using a discrete distribution, but later on I'm going to do one where we're using a continuous distribution. And so like what we have explained is how this half comes about. And this half comes about in that when we are summing absolute value, it's sort of like we are summing things 2 times, really, if you follow that. We started by splitting the differences from those that are positive from those that are negative, and then recognize that each distribution sums up to 1, so that difference is equal to 0. But then in this summation here, we split those where where this P is greater than Q, and then those where it is less. But when we think about it, we are going to be calculating absolute value, right? But before we even consider that, we are going to push this to go to the other side. Now, P minus Q was giving a negative, so when you put Q in front, this negative is going to disappear, which shows that there's equality between these 2 things. And that's why basically, if there's equality, that's like summing them twice. Yeah, and that's why we have actually put that half. I hope that makes sense. If you have any question, you can leave in the comments, and thanks for listening.